Hello class, so today we're going to be covering AND events. The examples are shown in slides 29 and 30. So for AND events, we have this formula right here. The probability of events A and B happening at the same time is the probability of A times the probability of B. So this is a formula that is given to you in the PowerPoint. So slides 29 and 30 cover some AND examples. 29 covers examples that are a little bit simpler, and then slide 30 deals with an example that is a little bit on the harder side. So example 1 on slide 29. Suppose you rolled a fair 6-sided die. We want to know what is the probability that the outcome is even and less than 5. So here, being even, the event that the number is even, let's call that event A, and the event that the number is less than 5, let's call that event B. So we have this formula up here, so we can go ahead and just quickly define what A and B are. So let's call A the event that the number is even. Let's call B the event that the number is less than 5. Then plugging what A and B are, probability of A, which is probability of even, and B, which is less than 5, that's going to be equal to probability of even times probability of being less than 5. So again, all that we're doing is plugging what A and B are into the formula to get what we have right here. So probability of being even. So we know that when we roll a die, we have 6 total outcomes. Out of the 6 of them, how many are even? 3. So the probability of being even is 3 out of 6. Now, probability of being less than 5. Again, we have 6 total outcomes. Out of the 6 outcomes, 4 of them are less than 5. So the probability that the number is less than 5 is 4 out of 6. If we multiply that through, we get 12 out of 36, which simplifies to 1/3. Now, we have this answer. We can also double check to make sure that our answer makes sense. So to do that, we can think about it intuitively. So for a given die roll, we have 6 outcomes. Out of the 6 outcomes, how many of them are even? So for even, we only have the numbers 2, 4, and 6. For being less than 5, we only have the numbers 1, 2, 3, and 4. Now, out of these, the shared commonality between even and less than 5 should be the number of outcomes are even and less than 5. So in this case, we have 2 and 2, 4 and 4. So that's 2 numbers that are shared between even and less than 5. So 2 out of 6, which simplifies to 1/3, which also agrees. And so by this, we've double checked that our answer makes sense. Moving on to the second example on slide 29, what is the probability that the number is odd and greater than 2? So again, let's say that odd is event A, greater than 2, let's call that event B. So without writing everything out like this, I'm just going to go ahead and plug it into the formula. So probability of being, well, let's see if it'll focus. Probability of being odd and greater than 2. That's going to be equal to probability of odd times probability of being greater than 2. Probability of odd, there are 3 out of 6 outcomes that are odd. Probability of being greater than 2, that's 4 out of the 6. So probability of being greater than 2 is 4/6. Multiply that out, we get 12 out of 36, which simplifies to 1/3. Again, does this make sense? We can double check it and see that the answer does make sense, because the only numbers that are odd and greater than 2 are 3 and 5 out of the 6 possible outcomes. That simplifies down to 1/3. Our third example on slide 29. What is the probability that the outcome is greater than 4 and odd? So here, let's call greater than 4 event A, and then let's call odd our event B. So here, probability of being greater than 4 and odd, that's equal to probability of being greater than 4 times probability of being odd. Probability of being greater than 4, we know that there are only 2 outcomes out of 6 that are greater than 4. Probability of being odd, 3/6, which gives us 6 out of 36, which simplifies to 1/6. Again, we can double check to make sure that this makes sense. So for the different outcomes that we can get for rolling a die, 5 is the only number that is greater than 4 and odd. And so there is only 1 out of 6 possible outcomes. So the probability that the outcome is greater than 4 and odd is 1/6. Now moving on to slide 30, we begin with this problem. You purchased 3 lottery tickets for which the probability that each ticket is a winning ticket is 10%. And so these 3 tickets are independent of each other. So buying one ticket doesn't affect your chances of winning for the second ticket. We want to know what is the probability that all 3 tickets are winning tickets. So here, let's look at what the probability of winning is and what the probability of losing is. So probability that one ticket wins is 10%, which means that the probability that a ticket loses is 90%. If we are looking for the probability that all 3 tickets are winning tickets, then let's see. The probability that all 3 tickets win, isn't that just the same as probability that ticket 1 wins and ticket 2 wins and ticket 3 wins? So probability that all 3 tickets win is essentially the same as probability that ticket 1 wins times ticket 2 wins times ticket 3 wins. By the AND formula, we know that we can just partition this. So probability that ticket 1 wins and ticket 2 wins and ticket 3 wins, that's the same as probability that ticket 1 wins times probability that ticket 2 wins times probability that ticket 3 wins. So again, we get that from this formula, P of A and B. We can rewrite that as P of A times P of B, which is basically everything that we've done right here. So now that we have it in this form, do we know the probability that ticket 1 wins? Yes, we do. We know that the probability that a ticket wins is 10%. So that's going to be 0.10. Do we know the probability that ticket 2 wins? Yes, we do. It's also 10%. Probability that ticket 3 wins is also 10%. This is the same as taking 0.1 to the 3rd power, which should give us a final probability of 0.001. So that's saying that the probability that all 3 tickets win is 0.1%. So there is a very, very small chance that you will get all 3 tickets that are winning tickets. Moving on to the second part of slide 30, what is the probability that none of them are winning tickets? And so for this one, it's going to follow the same exact steps, but now we're looking at the probability that all 3 of them lose. And here we know that the probability of losing is 90% for each individual ticket. So here we're following the same pattern. So probability that all 3 tickets lose, that's the same as probability that ticket 1 lose and ticket 2 lose and ticket 3 lose. And then by the AND formula, the red formula right here, we know that we can rewrite this as probability that ticket 1 lose times probability that ticket 2 lose times probability that ticket 3 loses. From here, we know the probability that 1 ticket loses is 90%, and since each ticket are independent of each other, it's going to be 90% for all 3 of them. This will give us 0.3 to the 3rd power, which returns 0.729 as our final answer. So the probability that all 3 tickets are losing ticket is 72.90%, which is a lot more compared to the probability that all 3 are winning tickets. Now finally, this example right here, what is the probability that at least 1 ticket is a winning ticket? So the word at least, whenever we see that word, we always want to take the complement. So again, remember the complement is P, A complement is equal to 1 minus the probability of A. So using this formula, the probability that at least 1 ticket wins, that's going to be equal to 1 minus the probability that none of them win. Which is 1 minus 0.729. The 0.729 is what we get from number 2. And our final answer should be 0.271. So the probability that at least 1 ticket wins is 1 minus the probability that none of them win, which is going to give us 0.271.